Good morning. Today I will talk about a real physics war story. In fact, the VIP2 experiment is now looking for the rebel electron which could violate the Pauli exclusion principle. But let's start this huge and charming story from the beginning. In a world ruled out by the Pauli exclusion principle, there could be a little group of electrons which jump among the atoms. The Nobel Prize Wolfgang Ernst Pauli declared in 1945, already in my original paper, I stressed the circumstance that I was unable to give a logical reason for the exclusion principle or to deduce it from more general assumptions. I had always the feeling, and I still have it today, that this is a deficiency. The impression that the shadow of some incompleteness here on the bright light of success of the new quantum mechanics seems to me unavoidable. In 2016, a small group of physicists built a strong machine which could give them enough power to identify these rebels. And this experiment is called VIP2. VIP stands for violation of Pauli. The rebel electron hunt continues. Let's move from this introduction to the index of this talk, in which I hope to give all you the possibility to understand well how much is important to investigate around this fundamental principle in physics and how this machine which we built is so powerful in this field. At the beginning, I will talk about how it is possible to investigate the Pauli exclusion principle with VIP2. I often will use the term PEP to say Pauli exclusion principle. I will talk about historical goals from Ramberg and Snow preliminary experiment to the VIP1, which was the first experiment. VIP2 is a significant upgrade of the experiment, very significant. And I will talk about the VIP2 experiment, purpose and apparatus, and at the end I will show you the calculation of a new upper limit for the Pauli exclusion principle violation of electrons in copper got with data acquired until July of 2017. So let's start talking about how it is possible to investigate this Pauli exclusion principle. In quantum mechanics, we know that the PEP can be formalized starting from two fundamental principles. All states, including those related to the identical particles, are described in terms of wave functions. And in the second point, we can say that the bosonic and fermionic states have a different behavior in relation to the application of the exchange transformation of identical particles. The bosonic states are symmetrical and the fermionic states are antisymmetrical. In a paper which is quoted in this slide, Messier and Greenberg, two important physicists, explain well how this second superselection rule does not appear as a necessary feature of the quantum mechanical description in nature. And this means that states of mixed symmetry could, in principle, exist. So we are talking about the possible existence of a particle states that follow a different statistic than the fermionic or bosonic one. From another point of view, Greenberg, which is one of the pioneers of the parastatistic theory and studies, in a conference of 2004, quoted possible external motivation for a violation of these statistics. Violation of CPT, violation of locality, violation of Lorentz invariance, extra space dimensions, discrete space or time, non-commutative space-time. So we have a lot of things to investigate around this very, very important, crucial principle. But what are we doing with VIP2? The experimental method of VIP2 is based on the introduction of new electron in a copper bar applying an electric current. This because, as the same Grimberg wrote in one of his papers, which is quoted here, whenever an electron is captured by an atom, a new state is formed that can have a certain probability of being a mixed symmetry state. This state is highly excited, and from its decay, one could observe a possible transition prohibited by the Pauli exclusion principle. So we have as experimental goal the search for X-rays from the Pauli exclusion principle violating transition. In the experiment, VIP2, the target is copper. So the energy transition which we are looking for is the K alpha 1, and the energy is 8.05 keV in copper, obviously. The eventually forbidden transition that we could observe if there is a violation should be an energy around 7.74 keV, which this energy has been calculated using a program which uses the multi-configurational Dirac-Fock method, which is a very, very precise method for this calculation. The difference of this energy is practically generated by an effect which is clear if you see below this slide the schematic of these violations. This is a normal transition, and this is the forbidden one because there are two electrons in the 1s level of the atom. So for the Pauli exclusion principle, there should not be one more electron that arrives here, but if there is a violation, this can happen. And this means that we have one more electron in the shell of the atom, and so one more screening effect, which is practically the motivation, the reason for this little shift which you can see here. So, let's start from the historical goals. The Ramberger's law performed an experiment in 1988 dedicated to measure X-rays emitted by a copper target crossed by a current, in the idea, obviously, to identify a possible violation. This is the schematization of the apparatus, and these are the spectra got in 2 months of data taking. From this spectra, with the data analysis, they have not found a violation, but they put a limit, an upper limit on the probability of violation of the Pauli exclusion principle in copper. And this is the limit, 1.7 for 10 to minus 26. This beta factor that you see comes from a statistic which is Ignatieff statistic, Ignatieff-Kuzmin statistic, and this beta square half represents the probability of violation of the Pauli exclusion principle. Okay, so this is the limit of this preliminary experiment. With VIP, we work to improve the Ramberger's law experiment, generating a complete new machine, which gave us the possibility to put a new limit, which at the end you will see it's very, very better than before. The improvements, the fundamental improvements were the use of charge-coupled device, which were detectors with a better resolution and covering more surface. This is a schematization of the apparatus. We have the possibility to put the experiment inside a very cleaner and low background area, National Laboratory of Gran Sasso, which is near Frascati, but it's a lab built inside a mountain, which is the Gran Sasso mountain, and so we have obviously a cleaner and low background area inside this mountain. And at the end, we have a better statistic due to the longer time taken, and this is because we take data for about 3 years, so this is more than what have done Ramberg and Snow. These are the two spectra. You can see the energy around 8 keV of the copper, which I have mentioned before. And what we have done is simply following the analysis, subtracting this spectra normalized in that region that you can see here. And in this range of interest for the possible violation, which is calculated using the energy of the forbidden transition, which I have shown before, and taking into account the resolution that the detectors have around the 8 keV of the copper. So we calculate this range of interest, and we subtract the spectra and count the X-rays in this part. And at the end, we have that there is no, we have not found any violation, but using the analysis, we have put a new limit, 4.7 to 10, for 10 to minus 29, okay? Taking into account that we are talking about a very, something that seems to be very low, but the number of electrons that we have in the universe is practically far from this value. So there are actually many possibilities to going on to find maybe something. So the thing is that it is a good result, because it's better than before of about 3 orders of magnitude. It's 10 to minus 29. Before it was 10 to minus 26. But the possibility to investigate around this principle is so important for the physics. And so we talked about a new machine which will give us the possibility to set a new limit and to investigate better on this Pauli exclusion principle for electrons in copper. This is the new setup, completely different, and obviously there are many improvements. One of these is the copper target, which is composed by this 2 strips, 10 centimeters for 1 centimeter for 50 micron. And the cooling system for the target, the water cooling system, which is very important, because when you turn on the current, the temperature should increase. So we built this to have a stable temperature respect to the detectors, because it should ruin the power of the detector. We have new detectors, the silicon drift detectors. You can see in this slide how much the resolution is better than before. These are the silicon drift detectors. These are the charge coupler device. We have the half of the full width maximum of the resolution. So the spectra, we can look better at this spectra, and we have less resolution, so the range of interest is less than before. And this is a great gain that we have. We organize these detectors in 2 chips containing 3 cells with an active area each of 100 millimeters square, cooled at 100 Kelvin using liquid argon to have the best performance of the detector. The energy resolution tested with a source of iron 55 and with a 25 micron of thick plate to have the energy of the titanium and manganese in practical, gives us a resolution around the 6 keV, which is the titanium energy, of 150, and we after confirmed that it's 170 EV around the 8 keV, which is the energy of the copper. So it's a great upgrade from the point of view of the resolution time, the resolution energy. Otherwise, we have also the SDD timing, because the SDD has the possibility to give a time resolution, which is around 400 nanoseconds. So it means that we can discriminate the background events. How we can do it? Building a veto system. We have before the mountain, because the lab is inside the mountain, so we have a low background and cleaner area in which the experiment is taking place. But using this 32 plastic scintillator and covering an angle that is more than 90% from the point of view of the target, we have the possibility to reduce more the background of about 1 order of grandness, which for an experiment that want to put a limit and to make a very, very precise calculation is fundamental. So it's a great, great result. And at the end, we can formalize all the improvements which this VIP2 will give us and put and sign as goal where we want to arrive, because we have a more compact system and this improves the asset terms. We have a new target, we have a different cooling system for the target to be sure that there is not too much variation in temperature on the detectors. We have a current that is better than before, because before was 40 ampere, now is more than 100 ampere. We are studying to flushing nitrogen to reduce radon in the barrack, because we are underground, and underground there is the radon which give us some background, but studying this possible flushing of nitrogen, we can put the radon outside and have less background. We have new detectors, we have a new Veto system which give us less background, and at the end we will have an acquisition of 3-4 years. Formalizing all of these with a table, we can find that the gain expected is more than 120. So we put as goal around 10 to minus 31. Okay? I can show you, this is the experiment. This is the setup box, some other stuff that are present inside the barrack, which is inside the National Laboratory of Gran Sasso. Only to show you how looks this experiment in the reality, in the real life. And at the end, as I promised before, I show you the calculation of the new upper limit for the Pauli exclusion principle violation probability. In fact, this comes from the data analysis until July of 2017. Obviously, the experiment is now running, so 3-4 years. So we start we started some years ago, and we are going on. Here you can see that this is the new limit that we fixed using this 81 days of current on the target, and you can see that this is a very great result, because with the VIP in 3 years of measurement we get this limit 10 to minus 29, and with only about 3 months of data collection, here we have a limit that is better than before. So the possibility to arrive to as goal is very, very real. At the end, what I can think about Paoli, the same Paoli could say from the sky, looking at us that are continuing and going on with this fight to investigate more around this important principle. Maybe VIP2, may the force be with you. And we hope that we can get very, very important results with this experiment. And for this reason, I thank all of you also for your attention.
Thank you very much, Luca. I invite also here Raffaella and Chiara. So now we go to some questions, discussions. You can ask them whatever might be interesting or whatever you might be curious on, not only on physics. You have seen they do different things, so particle physics, space, astrophysics, physics, and Pauli exclusion, so quantum mechanics. So yeah, I'll take another microphone. Okay, who wants to start?
There.
Very good. I have to leave you a microphone, however, though.
Okay, so my doubt is for Chiari, and it was about your reflectors. When you described the one that you sent to Mars, you said that it only have 5 centimeters of diameter. So how can you point your laser to it so you can receive the information back to Earth? How can you be so precise to reach that 5 centimeter?
Well, actually, the laser, when it is shot down from the station, let's say the orbiting station, of course, since it's a long distance, the laser does this. It opens a lot. So you have a big possibility on taking it, and you make calculations to take the right position. But imagine that at those distance, it becomes very big, like almost like a, not like this, but a little bit less than a soccer field. So it becomes very big at the end, so you have more chances of taking it.
Okay, thank you.
Next. Come on, you can also ask them curiosities about scientist life when you're young, scientist life, or whatever you have heard before. Guys.
Non ti sento, per questo mi sono avvicinato, non ti sento parlare, sento male.
I have just a question for all of you, because all of you studied physics or at least something similar. What was the hardest part in your study and in the bachelor and master?
For me, the chemistry exam is the worst one, but it was okay. Even if I'm experimentalist physicist, I have to follow, of course, a lot of theoretical courses. They are needed also to understand the developing part of the experiment. But theoretical courses for me are much more hard to study. So, but for this reason, I focus on another on a path more experimentalist. That's it. But everything is doable.
Well, for me, I wanted to study space. So I liked everything that I studied that was in space, but there was an exam called the Science of Constructions, and which is sort of all the forces, all the structural part of when you construct something for a shuttle or an airplane or for everything you have to build. And according to me, it was, I mean, I didn't like it, so it was quite hard. And as Raffaella said just a few seconds ago, that was the same for me. I mean, I choose all the other exams, so I did that, but then I choose all the rest to do for like specialization for me.
Taking into account that you want to do your best, okay? So it's, the thing is that it's hard how much you want that it's hard. Because if you want to arrive you want to be very strong in a field, you have to study. There is not period in a life of a physics in which you will not study. It's the basic one. You have to study from the university to go on. So there is not a real hard moment if you want to have the best results. The thing is that you can choose to go in a field which is not your field, and this could be difficult at the moment when you choose to move from a field to another field, because you have to study more, you have to arrive there. But if you think that in the entire career of physics there is a lot of things to study, I think that there is not a hard period, because it depends by what you want to do.
Luca has done 3 times the quantum mechanics exams, not because he failed it, but he wanted the maximum of the maximum of the maximum.
Yeah, yeah, it's right.
Okay, other questions?
Hi. On the Pauli exclusion principle,
Okay.
Was there much like theoretical reason to believe that violations might exist, or was it just to become more and more certain that the exclusion principle was correct?
Can you repeat? I listened not bad, not good. I don't-
So was there much of a theoretical indication that the Pauli violations might exist, or was the point just to become more and more certain that the exclusion principle was correct and accurate?
There are two, I think, 2 points of view. From the beginning, you have a principle which is practically tested, okay? Because the Pauli exclusion principle surely works. There is no possibility that it not works. The possibility is that there should be some mistake in nature for which it should not be okay every time, okay? So the thing is that, if I understand well the question, the thing is that what could be if there is a violation, that we add a new knowledge on the us books, and we know something else, we have to investigate about it, and we can discover maybe something else. Science is also not it's not possible to see before what you will find and how much what you find will be important in the future. But it's important not to look at what you will find, but look at what you can, what is not so sure at the end. It's sure, okay, but how much? How much is sure? I don't know if I have answer.
Yeah.
Okay.
However, there are reasons to doubt about its validity. If you and me change place in a string theory, when we come back, we wouldn't be the same. So this is called space-time non-commutativity. Okay, other questions? Good.
Hello. About the violation of the Pauli exclusion principle, I was wondering if the fact that on the first layer there would be another electron, would that impact the electrostatic interactions with other atoms, or yes, as they're nearer to the nucleus? Or
The question is, so you are wondering
what is the impact on the electrostatic force if there are more electrons on the first layer?
Yeah. Okay, at first you have to consider that these electrostatic movements inside the atoms are not so critical for the atoms itself, because there are a lot of electrons and sometimes you have ionization, so there is the possibility that you have more charge in the electric shell of the atoms. From the other point of view, surely the violation and to have one more electron should modify the electrostatic around inside the atoms. But it's also probably that this modification, because it's different than what we have observed before, because it's a violation, should be not high, because if it was a very high and important modification, probably we will see it there. But there should be the possibility that there is also some someone else effect which you have not prevented before, because it is a violation. It's everything new if you find it. So there should be a new mechanism, there should be new things that can modify it. But in principle, as I said before, the electric structure of the atoms, the electric shell, should be like when you can have a modification of the charge, okay, I think.
Thanks.
So atoms would be still neutral. You wouldn't have additional electrostaticity. Other question? Now we are approaching lunch, you're hungry. Then I ask all three of you, so if you would be, oh, wow. You should be, oh.
I have a question about the life of physics. I don't know, maybe it's a bit, how traveling is part of the life of physics? I mean, a facultative part or an important part?
At least for me, it's very important. I go to Chicago at least 4 times per year for a 2-week period, or a month period, or even 2 months. And I go at least to one conference, an international conference per year. We go around to perform also tests in other laboratories. I went to Zurich, Dresden, so we travel a lot, but depends also on the experiment you are working on. I mean, I work in an experiment in Chicago, so I have to work there. I have to go there. If I choose an experiment here, I wouldn't travel so much. So it depends. Particle physicists, I think, travel even more than other specialization, but maybe the other guys can answer to you.
Just a little part that I'd like to add is that she was talking about the conferences. So we travel a lot, especially for conferences, because conferences are important for the dissemination. When you discover something in science, then you have to disseminate it, to communicate, to let the other people know what is going on, what are your progresses, and what you're learning from your work. So it is important also for the dissemination. So traveling, especially for this one.
In my opinion, travel is not so important as meet different people, which is the very important thing. Because you have to think that in the future, when all of you will be a physicist, all of you will be different, and it's like to plant different seeds. So the ideas are different. So it's important to have the possibility to make a comparison with other people inside all the world, because there are many different ideas, and this is for me fundamental. So it's important travel, yes, to meet new people and to know other way of thinking about your field of physics.
Yeah, I mean, I wanted to say it's an important aspect of your life. It has a huge impact. You have to move a lot, often, and sometimes you have to go out for years, for example. But yeah, the main reason is to exchange ideas with your other researcher. Yes, of course, you can do it by Skype, but
yeah, but
it's more powerful or useful by meeting other people. So,
Thanks.
Okay, so we conclude. I ask you, each one of you, only 3 words, 3, not more. Pick up your 3 words. Why somebody should study science? 3. Who wants to start?
Because it's best.
3.
Because it's the best. 4
You
words, but
use
it's
4.
It's enough.
Next.
is challenging, is funny, and it allows to improve technologies for human knowledge. So it's important.
3 words.
I think
Look to look at the future. 4 words. Look at the future. I mean, science is very important, as all the fields are important for you. But if you look at the future, science can really help you to go there faster.
Okay, so thank you. Thank the three of you.